Welcome to the third chapter on choice and control of the logical foundations of cyber-physical systems textbook. After having seen continuous dynamical systems aspects in the previous chapter, we will now investigate discrete dynamical systems aspects in this chapter and right away begin to integrate the two to combine discrete and continuous dynamics. In continuous dynamics, we've already prepared for that. We have seen differential equations as a description of continuous dynamical systems, but also with their evolution domain constraints that are essentially handover points into cyber. Whenever the evolution domain constraint stops being true, we must have stopped before that happens already and let cyber take control. But of course, in today's chapter, we will investigate in what way and how cyber does take control and how the two exactly meet to solve their overall goal of describing systems that mix discrete and continuous dynamics. Today, in the modeling and controls domain, we will look at the important aspect of certainly understanding models of computation for cyber-physical systems, but also the core principles of discrete dynamics, in particular how they interact with continuous dynamics. You should think of the discrete dynamics as being fundamentally different than the continuous dynamics. The discrete dynamics is one step at a time computation, whereas the continuous dynamics varies very smoothly over time in comparison. Both phenomena are important. Think of what happens when you're driving a car. A lot of the behavior of a car will be how it continuously moves down the road. That needs continuous dynamical systems principles. But whenever you reach a sudden decision, such as, oops, now I need to brake hard because there's a car slamming on the brakes right in front of me, you need to reach a fundamentally different decision than the one you reached a moment ago. You will have to decide to brake. Or think of the moment when you decide to pull over and stop on the sideways. Or think of the moment when you're switching gears. None of these are a very continuous dynamical systems process. All of them are led with decisions and sudden discrete changes in the system's behavior. On computational thinking principles, we will understand the important role that non-determinism takes in these cyber-physical systems. We will see the computer scientist's secret weapon of abstraction and action. We will introduce and develop a very fundamental programming language for cyber-physical systems that will play an important, crucial role in the entire rest of the textbook. We will understand its semantics precisely and investigate the phenomenon of compositionality for hybrid programs in more detail. On the cyber-physical system skills aspects, we will investigate the operational effect and the operational precision. Overall, what we will be doing is, in order to understand what happens when we program cyber-physical systems, we not only program their physical aspects, we also program their discrete computational aspects. In particular, what we will be developing in this hybrid programs language, in which continuous dynamical systems features, such as differential equations, are to be thought of as what happens when physics evolves, whereas the discrete dynamical systems computations are to be thought of as the things that the computer does. In fact, this is an oversimplification. But for now, we can simply pretend that all the cyber aspects exactly correspond to discrete dynamical systems computation, and all the physics aspects directly correspond to continuous dynamical systems aspects. That's good pretense for now. Ultimately, we will see that even physical phenomena are sometimes best described by discrete dynamics, and even some very fast computational processes are best described by continuous dynamics. But for the time being, we will simply equate discrete with cyber and physics with continuous because it gives us a very easy starting motivation to work with. First, what we're going to do is gradually develop and motivate the language of hybrid programs for cyber-physical systems where we will identify a number of important phenomena in what programming languages for hybrid systems have to look like. We will also walk away with a number of very important lessons for modeling when working with hybrid systems. So let's first look at the easiest possible example you could think of a single point that's speeding on a line. For that, we saw a differential equation where the time derivative of the position equals the velocity, while the time derivative of velocity equals the acceleration. We might even have some evolution domain constraints attached to that, but never mind with that for now. Now, that's a beautiful model of continuous motion, but there's not a whole lot of cyber yet. For example, what it can do is, if the acceleration is 0, well, then it's going to be 0 all the time because there is no differential equation for it. That means the velocity will have some constant value all the time, and it means the position will keep on increasing over time. Of course, that isn't very safe. If you think of driving a car just by this differential equation, it would ultimately, for example, exceed any safety limit. For example, if m is the position of a stop sign, this differential equation will ultimately happily shoot past it. That's purely continuous dynamics. The question is, where does the cyber come in? Even if we add a evolution domain constraint to make physics stop, what's cyber supposed to do? Well, here's a fundamental operation for discrete dynamics. The change in acceleration, which discretely, at one instant of time, computes the current acceleration plus 1 and assigns that to the acceleration variable. This takes no time. So when you're at the current value, say 0 of acceleration, this computation will change the acceleration to be 1 from now on. Notice in particular that it's a great idea to separate concerns by saying continuous dynamical systems take all the time in the world and discrete dynamical computations consume no time at all. Because should you ever find yourself in a position where computations actually do take time, how about you just make the continuous dynamics explicit that happens while the discrete computation is still in process? But either way, we need to find out how such a discrete dynamical systems assignment meets with a continuous dynamical systems differential equation. And the easiest way how they could meet is by combining them with a sequential composition, semicolon. So first, we perform the discrete dynamical systems computation of adding 1 to the current acceleration in no time at all. And then we follow the continuous dynamics of a differential equation for a certain period of time. For example, that will increase the acceleration to some value. Then we'll keep on increasing the velocity, which will again keep on increasing the position. In fact, in a bit of a slanted way, but that's almost impossible to see in this particular picture. In other words, be careful with pictures. But just the operations we saw so far, discrete assignment, differential equations, and sequential composition, already enable us to write down much more interesting hybrid systems dynamics. For example, if we keep on repeating it like so, acceleration is -2, then we follow a differential equation for some time, acceleration is a quarter, after that we follow a differential equation, after that it's -2, and so on and so on and so on, a number of times. That can already describe behavior such as acceleration is -2 for some period of time, then it's changed to a quarter for some period of time, then it goes back to -2 and a quarter and -2, and let's just say ultimately it's 0, which is not in this particular system model, but it fits the example very nicely, where the velocity will keep on increasing because the initial acceleration was a -1, and then it increases not as much because it's just acceleration a quarter, then it decreases again, and it increases, and decreases again, and then let's just say we're stopped with that velocity 0. Which corresponds, for example, to this particular change in position, which in this particular example you already see fits well with the fact that m is a stoplight that we're not supposed to exceed position of. But Now, of course, that already gives us one question. One question is, well, if you've got all those differential equations, how long are we supposed to follow them each? And then if we've got all those braking, acceleration decisions, how can we properly check conditions on when we're supposed to do what? Well, programming languages have, of course, features for deciding. That's just the if then else condition. For example, if the velocity is less than 4, let's increase acceleration, otherwise let's brake. And when we're done with that, we follow a differential equation. This is a typical example of velocity-dependent control. So depending on the current velocity, we will decide to speed up or slow down. That sounds like a good thing. Of course, that's an oversimplification. Because really, maybe it's better to decide our acceleration and braking based on the distance to an obstacle. Think again of the stop sign. If the distance to the obstacle is more than a certain critical number, s, well, then we accelerate, and otherwise we brake. Well, but come to think of it, it might be even better to take both into account, to take a look at both velocity and position difference as an indicator for when we should be accelerating and when we should be braking. And that already identifies one important principle in this, that of iterative design. Whenever you're designing a system model, it's not necessarily a great idea to write down the most sophisticated model in the world right from the get-go, because the chances are that you might fail on understanding and analyzing it. Instead, it's much better to start with a simple design that you understand well, and once you have understood them well, move on and add more features into the design and work iteratively. And come to think of it, and in fact, this model is still not a very accurate one, because in reality you would also have some efficiency conditions. Think of fuel efficiency, passenger comfort, and all these features that will go into deciding whether you should be speeding up or slowing down. So we should only be accelerating if it's actually efficient to do so. But that brings up the other problem, that exact models of systems are quite unnecessarily complex, because I haven't even spelled out this efficiency condition. It's already looking more complicated, but not all of these features are actually safety critical, and it would be much better if we could simply decide on the basic decisions that our hybrid system can do, the decision that it might be accelerating or it might be braking, without being overly precise about what the exact conditions are under which the car is choosing what. That's where non-deterministic choice comes in. A non-deterministic choice operator will run the left program or the right program with no commitment on which particular side is chosen when. It just chooses arbitrarily. You can think of this like a slightly random thing. You just randomly make up whether you're running the left program or the right program. But just keep in mind that there's no actual probability commitment that tells you with what probability you choose the left or the right-hand side. But this model of the moving point now already captures very well that there are two possible decisions: to increase acceleration or to brake. And after that, we follow the differential equation. This highlights the power of abstraction. It's much better in your system models to only include the relevant aspects of the dynamics, and you simply elide detail that is there in your real implementation, but completely irrelevant for your particular analysis. And the advantage is exactly that both your model and the analysis of it become a lot simpler. And also that they do apply to more systems. Because by not having been overly precise about which of the two actions is chosen in what circumstance, many possible concrete implementations fall under this particular model. But there's a problem with it, all of a sudden. The problem is that the model got too simple. It just says, well, either I accelerate or I brake, but it doesn't say at all under what circumstance which side is chosen. That was part of the point, but we overdid it. Not every choice is actually always acceptable. It's not always acceptable to speed up. Your driver's license instructor might have told you so. Now we could go back to the if and else conditions and write down exactly under what circumstance acceleration or braking is chosen. But just we saw a moment ago that makes the models very complicated because all of reality will have to be reflected in our models that we are analyzing. That's not a whole lot of fun. Instead, we only retain what's the most important safety critical aspect. We will introduce tests into our language that will enable us to check conditions, the logical condition, for example, here, whether the velocity is less than 4. And this test on the velocity condition will make sure that the left branch can only be chosen if indeed the current velocity is less than 4. But because the right branch does not have any tests in it, it can always be chosen because the main operator, the non-deterministic choice, still is exactly that, a non-deterministic choice. Choose the left-hand side, or instead choose the right-hand side arbitrarily. But the left-hand side checks if indeed the logical formula v less than 4 is true in the current state. Well, okay, that's nice. What's supposed to happen if v is not less than 4 and we try to run it regardless because the non-deterministic choice happens to have decided to run the left-hand side? Well, then you just discard the failed execution attempt. In other words, failed runs are discarded, and you should think of this as backtracking. Any system run that fails a test is simply discarded in its entirety and not considered any further. For example, here, if we first test whether velocity is less than 4 and then increase the velocity by simply adding 1 to that, that only runs, well, if the velocity in the beginning was less than 4. But this hybrid program here first increases the velocity by 1 and then checks whether the resulting velocity is less than 4. In other words, the first one can only run if the initial velocity is less than 4, but the second one can only run if the initial velocity is less than 3, because it has to still be less than 4 even after we added 1. This also highlights the broader significance of non-determinism. Here we have a non-deterministic control that chooses the left or the right-hand side. The left-hand safety critical side of speeding up has a logical condition on when that's acceptable, but the right-hand side does not. It's non-deterministic selectively. Non-determinism is a tool for abstraction that enables us to focus on critical aspects of the system design. It is very helpful to enable us to just write down what's important about the controllers here in our own design, but non-determinism is also an absolutely crucial tool when we're trying to describe an environment about which we only have imperfect knowledge. Think of the car in front of you. You can't know exactly under what circumstance the car in front of you is speeding up or slowing down. You simply don't know the driver in front of you that well. And even if you've programmed that, you still don't know what it will be observing. So it's much easier to write down models in which the cars in front of you could have any arbitrary numbers of behaviors. But your own car has specific behaviors without being unnecessarily precise about which action is chosen in what circumstance. So what we've got basically describes one control cycle. In one control cycle, we will make an arbitrary choice to either accelerate, but that's only possible if velocity is less than 4, or to brake and then follow a differential equation. Now, if our car takes more control decisions and more control cycles, well, we need longer programs. For example, we could just copy-paste the program a bunch of times and put sequential composition semicolons in between, just as here. That already describes behavior such as, well, brake and accelerate and brake and accelerate and brake. The braking was always acceptable by these programs. It's just that in the acceleration case, it was very important that the condition on acceleration was met. But it would be very awkward if you would literally have to copy, paste, and repeat our controller as often as we're trying to execute the control loop because, well, for one thing, we don't even know how often our control cycle will keep on repeating if it is driving a car from the East Coast to the West Coast. So we need a repetition operator. Again, we could write down an exact while loop telling us exactly how long a controller is going to be repeated, but we already learned the lesson from the if and else operator. Being overly precise and when exactly our controller runs under what circumstances is just going to make us unhappy because we need to include all control details in it. Instead, we will be working with the non-deterministic repetition operator, the one that says, well, repeat this control loop any arbitrary number of times without making any commitment as to how often that exactly is going to be. So this now repeats the control loop inside the parentheses literally any natural number of times. Again, of course, it could decide, to break, that's always acceptable, and then speed up, then break, then speed up, and then break, and ultimately stop. After this gradual motivation into why we need the individual operators in hybrid programs, we'll gather everything we've got and design hybrid programs as a programming language more systematically. First of all, let's again write down a proper syntax for hybrid programs. Hybrid programs can have discrete assignments. This discrete assignment is the primitive for discrete dynamics, where we assign the value of a term e to a variable x by changing it at a discrete moment in time. What terms are possible as well, we've already seen in the previous chapter. This test statement is the primitive for imposing conditions on the state. So for a logical formula Q, testing Q will check whether the formula Q is really true at the current state. And remember, we will discard runs if that should not be true. The differential equation with the evolution domain constraint Q, again a logical formula, is the primitive for continuous dynamics, exactly identical to what we've seen in the previous chapter. We follow this differential equation within the evolution domain constraint Q for a certain period of time. The non-deterministic choice operator will run the hybrid program alpha or the hybrid program beta non-deterministically, where alpha and beta are recursively built like so. So think of the non-deterministic choice like you will either accelerate or brake, and I haven't quite committed which one yet. The sequential composition will first run alpha and then beta. So think of it like you will first speed up and then slow down, or think of it like first you will run a discrete controller and then you will follow a differential equation. The non-deterministic repetition operator will repeat the hybrid program alpha any arbitrary number of times. In fact, I would conjecture that you've seen these operators already, although potentially with slightly different notation. These are essentially regular expressions, just with assignments, tests, and differential equations as a primitive. But just like in regular expressions, either the left-hand side or the right-hand side, or first the left-hand side, then the right-hand side, or alpha any number of times, each of the choices and repetitions are non-deterministic, and also, in fact, the duration of the differential equations is non-deterministic. The next thing we need is not just writing down the syntax of hybrid programs, but also properly defining their semantics. Now, the semantics of terms was a function that mapped states to real numbers. Well, that's not suitable for what a hybrid program does. It doesn't just compute a real number and be done with it. The semantics of formulas was the set of states in which the formula happens to be true. That's actually also not the right thing for programs because they're not supposed to be true in some set of states. But what hybrid programs do is they change state. They take us from some old state into some new state. But come to think of it, they might even take us into multiple new states from the exact same old state. Why is that? Well, because of all the non-determinism involved. The non-deterministic choice between alpha and beta with, let's say, acceleration or braking might take us into different states. The non-deterministic repetition might take us into many different states, having repeated 0 times, 5 times, 100 times. And in fact, come to think of it, even the differential equation might already take us into many different possible states, depending on how long we follow. So the right semantics is one that takes us from an old state omega to a new state nu, but there could possibly be multiple of those new states nu for the same old state omega. So in other words, in general, this is going to be a relation of old states with new states. For the case of assignment, there's actually only exactly one output for every input, because the assignment, that's a deterministic function. It will change the old state omega to the new state nu in no time passing, where the old states and the new states only differ such that the value of the x variable in the new state is identical to the value that the right-hand side term has in the old state. And all the other variables, z, that are not x, are of course not supposed to change when we assign a new value to x. Differential equations take us from an old state omega to a new state nu, like we've defined last time. They will take us from the old state omega to the new state nu in some amount of time r, that is precisely the non-deterministic decision in it, where at the states that we reach at every time in between, we've stayed inside the evolution domain constraint Q, but also we fit the differential equation, x prime equals f of x, so the derivative of the value of x is exactly equal to the value of the right-hand side of a differential equation at this point in time, and that point in time, and that point in time. In other words, at every point in time, just like we've defined in the previous chapter. For tests, we will go from an old state to a new state. Well, but in fact, we'll only do that if the logical formula Q is even true in the old state. And what does the new state look like when we go there? It didn't change. It's the same one as before. So if in the current state the logical formula Q is true, we stay in the current state. What happens if you fail the test? Well, then there's not even a transition. There is no new state that we could transition to. Think of it this way. If you pass a test in the course, you're still the same person. Your state didn't change, but at least you're allowed to continue. But if you fail a test, you basically have the Gandalf effect of you shall not pass. This particular course of actions isn't working out for you if you fail a test, but you will have to resort to other non-deterministic choices, such as, well, next time, I guess I'll need to study harder to make sure that I pass the next test. For non-deterministic choices, we will go from an old state omega to a new state nu, and how we do that should be a function of what the hybrid program alpha should be doing and what the hybrid program beta should be doing. In other words, every transition that the hybrid program alpha can do to any new state nu1 is possible for the program that has a choice between the two. And every transition that the beta program could do to a new state nu2 is also possible for the program that has a choice, because the non-deterministic choice program alpha choice beta can of course today decide to run like alpha to any of the states it could get to, or instead decide to run like beta to any of the states it could go to. So for example, the program could have a choice to run from the old state omega this way around to the new state nu1, or it could choose to follow the funny squiggly red curve to the new state nu2 instead. For the sequential composition, it will also go from an old state omega to a new state nu by first running alpha to some intermediate state and then running beta from the intermediate state that it got to. So, for example, the system would run from omega by a differential equation to some intermediate state and then jump by a discrete change to the new state nu. But remember that the duration that it took for a continuous evolution was highly non-deterministic, so the whole transition could also be very short in comparison. For a non-deterministic repetition, we will go from an old state omega to a new state nu by repeating alpha. So we'll go through some intermediate state omega 1 that we got to by running alpha, then go to an intermediate state omega 2 that we got to by running alpha yet again, and go to an intermediate state that we got to dot by running alpha to some final state nu. And any states that we could get to by repeating alpha any number of times in this way is reachable by running the repetition operator alpha star. So for example, follow continuously, then do a discrete change, and follow continuously, then do a discrete change, then follow continuously. A typical high resistance behavior. With these transition system diagrams that I've shown you, and the examples on the right-hand side, we have, although admittedly in pictures, essentially defined the semantics for hybrid programs. Before we get more precise about what they really are like, let's first understand how we read the sequential composition, repetition, and choice transition diagrams in case we have a more complicated hybrid program that consists of multiple. Well, how we would do that is, for example, for the sequential composition that is repeated, we will essentially plug the sequential composition picture in for the transition within a repetition picture and put it in here again and in here again. That leads us to this description. From an old state, we go via an intermediate state we got by running alpha to an intermediate state omega 1 that we got to by running beta. Again, through an intermediate state we got to by running alpha, running beta to an intermediate state from which, again, alpha and beta and alpha and beta and alpha and beta and alpha and beta. In other words, alpha semicolon beta star will repeat any number of repetitions of first alpha and then beta and then alpha and then beta, always interleaved. Whereas a non-deterministic repetition of a non-deterministic choice will plug this picture in for alpha here and here and here, which will lead us to the following transition diagram. Where we start, we could run alpha choice beta once. For example, we could run beta. We could run alpha choice beta again. For example, we could run alpha. We could run alpha choice beta again. For example, we could run beta, and so on any number of times. But of course, at this point, it should be apparent to you that while these transition diagrams are very useful to support our intuition, we also have to become very precise about the mathematical characteristics of it. So let's define exactly that. The true semantics of a hybrid program, the semantics bracket function, is a function that associates with every hybrid program a relation from initial state to final state. In other words, a set of pairs of states, initial state, comma, final state. For example, the meaning of an assignment is the relation described by the set of pairs of states, old state omega and new state nu, that are actually identical except for the value of the variable x, which is such that the value in the new state nu of the x variable is identical to the value in the old state omega that the right-hand side term had. In other words, put the value on the right-hand side, evaluate it in the old state, put the value in the new state at the variable x. The meaning of a test is the relation described by the set of all pairs that don't change state, so go from the old state omega back into the old state omega, but only do this if in the old state omega the logical formula Q was actually true. In other words, this actually implicitly says that the set of states we could go to from a state omega in which the formula Q is not true is actually the empty set, the U shall not pass condition. The semantics of a differential equation is the relation described by the set of initial states and final states for any solution of the differential equation of any duration that's a real number greater or equal to 0, such that the state at the initial time 0 is where we start, and the state at the final time r is where we end. In other words, follow a differential equation from the initial time to the final time for any duration. Fit the differential equation to every moment in time in between. The meaning of a non-deterministic choice is such that the set of all transitions that alpha choice beta can do, it's just the set of all transitions that alpha can do, union the set of all transitions that beta can do. Makes sense, right? The behavior that a non-deterministic choice between alpha and beta has, of course, is all the behavior that alpha could do, union all the behavior that beta could do. The meaning of a sequential composition is the composition of relations of alpha and beta. That means alpha semicolon beta can go from an old state omega to a new state nu whenever for some intermediate state mu the alpha program can go from the initial state omega to the intermediate state nu, and from this intermediate state can the program beta go to the new state nu. The meaning of a non-deterministic repetition operator is that it has all the behaviors that alpha has any number of times, which can either be defined as the reflexive transitive closure of the relation that corresponds to the meaning of alpha, or it can be defined as the union over any natural numbers of the behavior of alpha power n, where alpha power n is just the n-fold sequential composition of alpha. So alpha, semicolon alpha, dot, 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 semicolon alpha, exactly n times. In other words, the behavior of alpha star is exactly the behavior that alpha repeated 0 times could have, union the behavior that alpha repeated 1 times could have, union the behavior that alpha repeated 2 times could have, union the behavior that alpha repeated 3 times could have, and so on. And remember, just like last chapter, we can become more precise about what it means to solve a differential equation. It means that the value of the x prime variable at any time z is exactly the time derivative that the value of x over time has at that moment in time. In other words, this time derivative at least has to exist, otherwise it's hard to make sense of what it means to satisfy a differential equation if there is no time derivative. At the time z, the value that the solution has satisfies the formula x prime equals f of x and the evolution domain constraint q, where, remember, the value of x prime exactly is the time derivative that x has at that moment in time, and the value of the right-hand side of a differential equation is evaluated. In other words, if we plug in the time derivative for x prime, then x prime equals f of x should be met at every point in time, and the evolution domain constraint should be satisfied at every point in time. And the state isn't changing in any other way. That means at any moment in time, the state agrees with the initial state, except, of course, for the value of the x variable, which is changing by the differential equation, and the value of the x prime variable, which is implicitly changing with the differential equation. Notice here how the semantics is perfectly compositional. The meaning in each of those cases is a simple function of the meaning of the pieces. For example, the meaning of alpha choice beta is just the simple union function applied to the meaning of alpha and the meaning of beta. The alpha semicolon beta meaning is just a simple relation composition of the meaning of alpha and the meaning of beta. And the meaning of the repetition operator is just a reflexive transitive closure, also defined in other ways, of the meaning of alpha. Likewise, the meaning of assignment is just a function of the meaning of the variables and the meaning of the terms. The meaning of a test operator is just a function of the meaning of the formula, and the meaning of a differential equation, as we just talked about, is a function of the meaning of the right-hand side and the meaning of the derivative variables x prime. In other words, this is a compositional semantics. The meaning of a big program is a simple function of the meaning of the pieces. So even if we have a terabyte of a hybrid program, these definitions already tell us exactly just by plugging in and plugging in and plugging in what the meaning of a very complicated program looks like. Now let's just take a moment to review some of the usual naming conventions you will find, just to make sure you're not misreading things. X, Y, Z are usually used for variables, E tilde are usually used for terms, P and Q are usually used for formulas, alpha, beta are usually used for programs, C is usually used as a constant symbol, F, G, H are usually used as function symbols, and P, Q, R are usually used as predicate symbols. The last you will actually not find a whole lot yet, but we will eventually make use of them. However, just be warned that that's sort of the mathematical convention in theory, but in CPS applications, all bets are off because your names will very likely follow the application. For example, X is a canonical name for a position, V canonical for velocity, A is canonical for acceleration. Also, our notational conventions, just to make sure we're cutting down on the number of parentheses, but you can still read hybrid programs unambiguously. We'll still make sure that unary operators, including the non-deterministic repetition star and logical negation, but also the quantifiers for all and exists, bind stronger than binary operators such as and, or, implies, and bind stronger than or, which in turn bind stronger than implication and by implication. Semicolon bind stronger than non-deterministic choice, and also sometimes you'll need to know that arithmetic operators all associate to the left, while logical and program operators all associate to the right. For example, these imply that for all xp and q actually means for all xp and q. Likewise, for all xp implies q actually means if for all xp is true, then q is true. Alpha semicolon beta choice gamma means alpha semicolon beta with a non-deterministic choice of gamma. And likewise the other way around, alpha choice beta semicolon gamma actually means alpha non-deterministic choice with beta followed by gamma. And also alpha semicolon beta star actually means alpha semicolon and then beta repeated. Also, P implies Q implies R because of the association to the right actually means P implies Q implies R. But also implication and by implication themselves expect explicit parentheses. For example, these expressions down here are considered to be illegal because, well, I don't even know how to read them. So now I think it's time to look at a few examples for hybrid programs just to get a better sense of how they operate and make themselves familiar with how to write down such basic systems models as hybrid programs. Here's a canonical one, a simple robot controlling, then driving repeatedly, where control is defined like so, this non-deterministic choice, and driving is defined like this. Let's unroll what its transition structure looks like. The topmost operator is the non-deterministic repetition. So we're in some initial state, and we decide on whether we would even like to run the non-deterministic repetition at all. Let's say we do. If we do this, we execute the choice that we find in the control, the choice between the left or right option. Let's arbitrarily decide that the left choice is being executed. But in the left choice, we first find the test of the QA condition that we need to satisfy. Otherwise, we cannot actually execute this one. Suppose it's true in the current state, then we can successfully run the assignment that happens right after. Then we're done with the control part. Go into the drive part. That begins with an assignment of 0 for the clock variable t. And then we follow the differential equation for some arbitrary amount of time, respecting the velocity and time constraints. The time is at most time epsilon. Having done so, we're done with driving, and we can again decide whether we'd like to repeat the non-deterministic repetition. We could either stop right now or try the whole thing again. Let's do the whole thing again. So we go back. Of course, it's a new state, but we're at the same place of running the hybrid program, where we begin with the control that has a choice between left and right control action. This time, let's say the right choice is the right one to be used. So we execute the right choice, which begins with a test. Again, at this point, the logical formula QB needs to be true, otherwise we cannot actually go on. Then we change the iteration to be minus B. Then we go into the drive part and reset the clock variable to 0. Then we follow the differential equation for a certain period of time. And then again, we find ourselves at the position where we need to decide whether we want to repeat again. And let's suppose at this moment we simply stop. Notice, the non-deterministic choice between these two options is always available and can be made arbitrarily. But in effect, the left choice is only a possible one if the logical formula QA is true at the moment, because otherwise we will fail the test right away. It's by backtracking, the other choice is the only possible one. The right choice, de facto, is only really effective if the logical formula QB is true at the moment. In other words, when you're designing hybrid programs, it's important to think about making sure, are there states where both of those logical formulas are true? Because then there's a true non-deterministic choice between acceleration and braking. Or are there states where none of the two is true, which are slightly awkward, because that means it implicitly says that your control is stuck, which you need to be very careful about. Now, why didn't I give you more operators of hybrid programs? I only gave you the primitives of assignment, tests, differential equations, non-deterministic choices, sequential compositions, non-deterministic repetitions. But I'm sure in your programming languages you can think about many other operators that are fun to be used. For example, the if and else operator and the while loop. Well, I didn't give them to you because you've got them already. Take a moment to think about whether you can define the if then else operator out of the primitives I gave you, and whether you can define the while loop out of the primitives I gave you. This is an awesome moment to pause the video for a second. For example, if Q alpha else beta, well, at a high level of abstraction, I guess it's running either alpha or beta. That sounds like a choice to me. But of course, it's only supposed to run alpha if Q is true. And it's also only supposed to run beta if Q is actually false. That's precisely this hybrid program. There's a non-deterministic choice between running test Q followed by alpha and running test whether not Q is true followed by beta. In a similar line, while Q alpha, well, that's repeating alpha, right? That sounds like a non-deterministic repetition, but we need to limit the non-deterministic repetition a bit more because it's only supposed to run alpha again if Q is still true, but it's only supposed to stop when Q has become false. That means precisely it's a non-deterministic repetition, arbitrary number of times, that begins with a test whether Q is true, followed by alpha. Can do that any number of times. It can stop at any moment in time, but the stopping will only be successful if ultimately the test whether or not Q is true succeeds. In other words, the primitives I gave you in hybrid programs again enable us to define every other programming language construct you could possibly ever think of. It is useful for us, just like we didn't add minus subtraction into the language, and just like we didn't officially use by implication in the language. It's useful for us to make sure that we only have to deal with a limited number of operators in theory, even if, admittedly, if then else conditions are very useful in practice. But in hybrid systems, it's actually often useful to have weaker notions than if and else's for reasons of abstraction, to describe choices where, the left-hand side is only possible if Q, but the right-hand side breaking would always be fine, or things like that. Let's take a look at another example. Suppose you have a robot that's following a sequence of arcs and lines in the two-dimensional space. How would you describe this behavior with a hybrid program? Think about it for a moment and pause the video. How we describe this is by a non-deterministic repetition, because we don't know how many line and arc circles the robot will be following. Where every time we first run a discrete controller that will change the angular velocity to -1, 1, or 0, depending on whether it's going left, right, or going straight. And then we follow the differential equation of circular motion, where the circle, of course, is a degenerated line if the angular velocity is 0. Now, that won't necessarily be safe for a robot to really arbitrarily decide to move left or right or straight on. So in reality, of course, you will want to prefix each of those cases with logical formulas that are checking under what circumstance the decisions would be safe to do. Let's go back for a second to the moving point and the moving line example where we've seen this replicated controller. And let's just make our lives easier by deleting some stuff out of it. And it just looks like so, which looks like a much better and easier model. But beware that we've done something quite catastrophic. What we have indirectly done is to say we run this, follow the differential equation after having increased the acceleration, but then we test that the velocity is less than 4, and then we increase the acceleration again. We follow the ODE, but we test that the velocity is still less than 4, increase the acceleration, and follow the ODE again. These tests are pretty dangerous because they're not part of a non-deterministic choice anymore that leaves around other options, but all of a sudden these tests impose assumption conditions on the current state. I'm assuming at this moment that the velocity is less than 4, and thereby I've truncated and made impossible any behavior of a system where indeed after having accelerated for a little while my velocity has become too large. In other words, this is a bad model. The hybrid program assumes the test to pass after each ODE. No other choices are available anymore. Which means for you, please make sure that you don't let your controllers discard important control cases. You can check on them, but don't discard them. So now let's summarize what we've learned in today's chapter. We've seen the syntax of hybrid programs with discrete assignments for discrete computation, tests for checking conditions on the state, differential equations with evolution domain constraints for continuous dynamics, non-deterministic choices between two hybrid programs alpha and beta, sequential compositions for running the beta program after the alpha program, and non-deterministic repetitions for running, for example, control loops any number of times. We've also defined the semantics of hybrid programs unambiguously by defining for each hybrid program, by induction on each of the cases, that the program could be constructed like a behavior described as a relation, meaning a set of initial final state pairs